All right, good morning, everybody. So I want to I want to talk about implementing an array-based stack today. So instead of using the list-based stack that we had last class, we're going to implement an array-based stack. Now, when we do an array-based stack, you have to take care of all of the memory management. Well, not all of it. You have to take care of a lot of the memory management yourself. So you're not relying on the list now to take care of making space for extra elements in the stack. Before I do that, though, I want to show you one application of using a stack. So you should have seen a recursive method in CISC121, or you should have seen recursive functions in CISC121. So remember, a recursive function is a function that calls itself, right? So in Java, you can have recursive methods. So you can have methods that call themselves. One of the problems with using recursion is that you're often limited in the size of the problem that you can solve because of the way that your language actually does the recursion. So here's an example of a simple recursive method in Java. So you would never actually write this method in Java, right? So this just calculates, this recursively calculates 10 raised to the power n, right? So that's all it's doing. So it's basically multiplication, right? Now remember, in a recursive method, you need a base case, right? So that's the case where the method or function stops calling itself, right? So if n is 0, then 10 raised to the power 0, well, that's just 1. So that's easy. I can return 1, right? If n's not 0, so I'm going to assume n's positive, right? If it's not 0, then you just compute 10 to the power of n minus 1, right? And then multiply that answer by 10. Right? So how do you compute 10 to the power n minus 1? Well, you just call power of 10 and let it take care of it. Right? So eventually this term here reaches 0, right? And so you can plug in a 0 here eventually, right? And that'll give you 0, you can plug in 0, you can plug in a 1 here eventually. That'll give you 10, right? And then it'll return, right? So the previous recursive call knows that that answer is 10, so it'll multiply it by 10 to give you 100. And then that will return. That'll be 100, right? Times 10 is 1,000, and so on, and so on, and so on. Right? Now, in a language like Python, Java, or C, the way this actually works is as follows. So in my main method, I'm going to call power of 10. Right? So somewhere there's a variable called x, right? Somewhere in memory. Right? The value of x is going to be whatever power of 10, 3 returns. Right? So this should be 1,000. What happens in recursion is that so in recursion, you call the caller calls the method, right? They call the recursive method. What happens is somewhere in memory that method runs. Okay? So associated with that method are the parameters of the method, right? So remember, we have a parameter n, and we have a local variable called result, right? So in the memory that this function or method is running in, right, we have n and result, right? So when I call the power of 10 the first time, I know that n is 3, right? Then the method does some stuff, right? And what does it do? It checks the base case, right? And then goes to the recursive case. Right, so the recursive case says the result is 10 times power of 10 n minus 1. Right? So in the result, right, that's the result, right? Which is a recursive call to power of 10. Right? Now, when you make the recursive call, right, the recursive call to power of 10 does not run in the same block of memory. It runs in a new block of memory. Right, so another version of power of 10 appears. Right? It has its own parameter n, and it has its own local variable result. Right? So now this is going to run with n equals 2, so that's going to recursively call power of 10, 1. Right? It's another recursive call, so a different version of the method appears. Right? And runs with n equals 1. Right? What does that do? Well, that ends up in the recursive case and calls power of 10, 0. Right? Again, another version of the method appears in memory. Right? So when you call a recursive function or method in Java, right? The function or method is not running in the same memory space every time, right? A new instance of the function or memory appears, right? Each new instance has its own copy of the parameters and local variables, right? And the method runs in its own little block of memory, right? Every time you call another method, a new chunk of memory appears that runs that method. Right? Okay, now what happens? So in that last recursive call, n is 0, so that's the base case. So we actually know the answer now, right? We know the result is 10, right? Now that it has a result, it returns, right? So that 1 goes back up here to the previous recursive method, right? So we're going to transfer that 1 up to here, and this method's going to go away because it's done, right? So the 1 goes up, this method goes away, right? That answer becomes 10, right? Now this one can return back to its caller, right? So that 10 can get copied back up to here. This method can go away, and that answer can become 100, right? That one's done, so it can return back up to here, right? That will become 100. This method can go away, and that becomes 1,000. Whoa, what happened? Uh-oh. Oh, there. Okay, good. Right? That becomes 1,000. Now, this method's finally done. So it can return 1,000 back to the original caller, and then it can go away. Right? And now all the memory that was allocated to these different versions of power of 10 has all been released back to the, in this case, the Java virtual machine. Right? So let me just reverse that process for a second. Right? So I'm going to reverse the process, right? So there's something appears, right? Something appears, something appears, something appears, then they all go away, right? So this picture here, or this sequence of steps, right? You're just pushing stuff onto a stack. It's just the stack's growing down, right? When you're returning, you're just popping stuff off a stack, and the stack's growing up, right? And that's exactly what happens inside of a language like Java or C or Python, right? There's something called a call stack, which is what I just showed you, right? So to implement a recursive method, you don't have to rely on the Java or Python or C, right? Putting methods onto the call stack or putting functions onto the call stack, right? You can take care of everything that's going onto a stack yourself by using a stack. And that lets you turn a recursive method into an iterative one, right? Okay, so the basic idea is I need to push whatever information onto a stack to remember what needs to be done when the recursive method returns. Right? Okay, so in power of 10, what needs to be done when each recursive call returns? Right? So and every time you return from a recursive call, right? Right, so do we multiply the return value of the recursive call by 0? Well, no, that doesn't make sense, because that's going to make the answer 0, right? Do we multiply the return value by 1? Well, no, we don't do that either, because we want to multiply by 10 every time, right? So every time you return the value from a recursive call, the previous version of the method multiplies the answer by 10, right? So it looks like we're going to have to do something when we turn this into an iterative method to multiply by 10, right? So each recursive call that's not a base case pushes a 10 onto the stack, right? Because we're going to use the stack to remember what needs to be done every time, right? Now, during each recursive call, what actually happens to the value of n, right? So each time we call power of 10, n goes down by 1, right? So n decreases by 1 every time, right? So what's this going to look like? Okay. So I'm going to make a stack, right? And as long as n's not equal to, as long as n's greater than 0, right? So as long as I'm not in a base case, I'm going to push a 10 onto the top of that stack, right? Now I need to make sure that this loop ends, right? So I'm going to decrease n by 1 each time, right? So that what we're doing here is we're basically emulating or trying to emulate what the virtual machine was doing anyway. Right? I push a 10 onto the stack to remember I have to multiply the result by 10, right? when I make the recursive call, n goes down by 1 each time. Right? So what this ends up doing is it just ends up pushing n tens onto that stack. Right? Now, the recursive call that reaches a base case results in a 1. Right? So when you reach the base case, you start multiplying the answer by 1. Right? So there's your base case. The result's going to be 1. Right? Now I just unwind the stack. Right? So how do I unwind the stack? Well, I just pop the stack until it's empty. Right? Each time I pop the stack, I take the answer and multiply it into the result. Right? So while the stack's not empty, right, pop the stack and multiply it by the result, and then put it back into the result. Right? When that's all done, you end up with 10 to the power n, and so you can return that. Right? So there's an example of turning a recursive method into an iterative one using a stack. Right? So this is a very simple example. Right? This is about as simple as you can make it. If I ask somebody to implement a method called power of 10, you would just write a little for loop. Right? You wouldn't actually go through all of this trouble. But if you had a very complicated recursive method, right, that you were asked to turn into an iterative one, right, you can always use an approach similar to this to get the same result. Right? And in fact, that's one of the ways that you turn a recursive method into an iterative one. Right? OK, so I'm not going to try to do anything more complicated than that. So that's just showing you what you could do to convert a recursive method into an iterative one. Right? So that's way too complicated for the problem that you're actually trying to solve. Right? You would just write a for loop. Or you'd call math.pow. Right? But it illustrates the basic idea of using a stack to convert a recursive method to an iterative one. There's not another example. I took the other example out. Right? Maybe later on, towards the end of the course, we'll try to convert I'll try to convert a recursive method that has no obvious iterative one into an iterative one using a stack. Right? For now, though, let's move on and try to implement our own stack using an array. All right, so in the previous version, we used a list, right? When you use a list, everything's easy, right? When you push something onto the stack, you just add something to the end of the list. When you pop the stack, you just remove the element at the end of the list, right? Now, you can do the same thing with an array, right? You can add an element to something like the end of the array. Not quite the end of the array. You want to add it to the end of the stack, right? OK, and similarly, right? With a list, you can keep on adding as many elements as you want to the end of the list, and the list just keeps on growing, right? To hold all the elements that you add, right? Until you run out of memory. You can't do that with an array, because an array holds a fixed number of elements, right? So when the array becomes full, you've got a problem, right? You can't push any more elements onto the stack if you're using an array, and the array's full, right? So now you have to solve the problem of, well, when the array is full, I have to reallocate a new array, right? Copy all the elements into the new array, and then use the new array for the stack, right? All right, now instead of adding and removing from the end of this, all right, so a list has something, right? So a list knows where the end of the list is. An array does not know where the last element in the array is, right? So you're going to start out with an array of, say, size 10, right? And I want to put something into the array, right? I want to push the first element onto the stack, right? So I want to add it at element 0, right? I don't want to add it at the end of the stack, at the end of the list, right? I want to add it at element 0. When I push something else onto the stack, I want to add now to the array at index 1, right? But not, again, at the end of the array. So I need some field that marks where is the top of the stack in this array. Okay, so I'm going to make a class called int stack, right? So this is just a stack of integers, of int values, sorry. I'm going to have an array to hold the int values, right? So that's going to be my storage for the stack. And then I'm going to have a field called top index. So that's the index in the array where the top element currently resides. So if the stack is empty, there is no top element. So top index will be -1 to indicate that we have an empty stack. Right? The default capacity, that's just going to be the size of the array that the constructor is going to create. Right? So unless there's some constructor that makes a stack of a specified capacity, we're going to use a capacity of 16 to begin with. Right? So when we make the empty stack, we make our array, right, with the default capacity. Top index is -1, right? So we know that the stack is empty. Right? That's the picture of what what our stack representation looks like at this point in time. Right? So when I make a new int stack, I have an array of size 16. All the elements are 0, because that's what Java does. Right? When you make a new a primitive array, it initializes everything 0. And the top index I've got is -1. Right? So if I was trying to index into the array using top index, I would get an exception, right? Because there is no element at index -1. All right, so how do I push a value onto the stack? Well, to push a value onto the stack, I want to insert here, right? Which is 1 plus the top index. Right? So I'm going to increment the top index, right? Add 1 to it, and then just set the value in the array at that index. Right? So, and start out with an empty stack, push a 7, right? Top index becomes 0, right? I increment top index so that we go from -1 to 0, and then I set the element at index 0. Right? And now top points to the element at, the top now has the value 0, right? To indicate that the element is sitting at index 0 of the array. All right, now I push another value, right? So I'm going to increment top index by 1, and then set the value in the array at index 1. Right? Push another value. Oh, I didn't push another one. All right. How do you pop a value from the stack? Well, I know where the top index is. I know where the top element in the stack is. So I copy the top element in the stack. Right? Do I have to copy it? Yeah, I get the value at the top index of the array. Then you decrease top index by 1 to indicate that you're popping a value, right? And then you return the value. Right? Notice that you don't actually have to modify the value that was stored in the array. So let's look at let's take a look at that picture here. Okay, so I'm going to push a 7 and push a -5, right? So we have an element at -5 and top index is at 1, right? Then I'm going to pop the top index. I'm going to pop the value on top of the stack, sorry, right? So I'm going to copy -5, right? I'm going to decrease the top index, so now the top of the stack points at the 7, right? And then I'm going to return the -5, right? You don't have to do anything to the old -5 that's sitting there, right? Because the next time you push something onto the stack, you're just going to overwrite it anyway. The other reason you don't have to do anything about it is because there's nothing special about 0 in the stack. Right? You can push a 0 onto the stack. So there's no value you can put into here to indicate that there's nothing there. Right? So in a Java array, if you have an array of int, you have to put in an int. Right? You can't put in null, because there's no such thing as a null primitive. Right? So you have to put in some value in the array no matter what. Right? So there's no way you can create a special value to indicate that there's nothing there. So what does pop look like? Well, you can't pop an empty stack, right? So if the top index is -1, there's nothing in the stack, right? So you should throw an exception. Yeah, okay. In Java, there's a class called Java util.emptyStack exception that you can use. I think the notebooks just uses, I don't remember what the notebook uses. But it's not empty stack exception. It uses some other exception. All right, so check if the stack is empty. If it's not empty, I can get the element that's sitting at the top of the stack. Right? At the bottom, I'm going to return that element. Right? But before I return that element, I have to adjust where the top of the stack is, right? To indicate that I've popped an element from the stack. So pop's not too bad, right? It's harder than the one line that was in the list-based implementation, right? But otherwise, it's not too bad. All right, so here I've got a stack that's almost, I have a stack whose array is almost full, right? So the capacity of that array is 16, right? The top index is currently at 14. right? So I've got one more free spot where I can push something onto this stack, right? Okay, so when can I safely push something onto the stack? Well, when the length of when the top index is less than the length of the array minus 1. Right, so let's go back here. Right, so the length of the array is 16. Right, 16 minus 1 is 15. Right, I can safely push onto the stack as long as the top index is less than 15. Right, less than 1 minus the length of the array. Right, so if the top index is less than the array length minus 1, right, increment the top index and then set the element in the array. Right, so that's pretty easy. Now the problem is, what happens if this if statement is not true? Right, so what happens if the top index is equal to the array length minus 1? Right, so if the index is equal to the array minus to the length of the array minus 1, the array is full. Right, so I'm out of capacity to hold any more new elements. Right, and so what I want to do is I want to increase the capacity of that array, but I can't. Right, so in Java, there's no way to extend an existing array. Right, the only thing you can do is you can make a new array with greater capacity. Right, so I can make a bigger array. The question you have to answer is, well, how much bigger is this new array going to be? Right, I want to add one element, so do I make the array one bigger? Right, do I make the capacity of the new array 1 larger than the current capacity? Do I make it 2 larger? Do I make it 10 larger? Do I do something else? Right? So that's one question we have to figure out an answer for. Once you've got the bigger array, I've got to copy all the contents of the old array into the new array. Right? Because if I don't, I'm going to lose all the elements in my current stack. Right? So now I've got to copy everything into the new array. And then finally, I have to tell this stack object that your I have to tell the stack object that your array now refers to a new array. Right? So I have to set this .arr to refer to the new array. Right? So now I've got a stack with more capacity, or I have an array with more capacity. Right? So now I can just go ahead and push the element onto the stack. Right? But I have to do all of this first. Okay, so I need to make an array with more capacity, right? So technically, you can do anything here, right? As long as you increase the capacity. So for example, I could write this array length plus 1, right? And increase the capacity by 1, right? Here, I'm multiplying it by 2, right? So I'm going to double the capacity of the existing existing array. Right, so let's just go with this for now. So I'm just going to double it for now. I'll come back to this in a moment. Right? I now have to copy the contents of the old array into the new array. Right? So I have to copy the contents of the old array into the new array. Right? At this point in time, the only way we know how to do that is to use a loop. Right? So I'm going to loop over the elements of the old array. Right? How long is the old array? Well, it's just this array.length. Right? Each iteration of the loop, I just assign new array I. I assign the value this array I. Right? So I just copy element by element into the new array. Right? Now finally, I can set the field this array to refer to the new array. Right? Now what happens to the old array? Right? So the old array in Java, right, as soon as you no longer have a reference to the old array, right, the Java virtual machine can eventually come along and clean up the memory that was associated with the old array. Right? The only thing that has a reference to the internal array is the stack object itself. Right? So if you write this array equals something else, there's no reference to the old array anymore. Right? And now the garbage collector can come along and clean up the old array. And then finally, I can push the element onto the stack. Right? So if you wanted to, you could rewrite all of the push code. Right? So I could rewrite these 2 lines. Right? But it's easier just to recursively call push. Right? Because that's what this is doing. Right? This is a funny push method. Right? It's actually recursive. Right? So normally, right, when there's capacity in the stack, it just does something and it's done. right? It just increments the top index, sets the element at the top index, and you're finished, right? When you have to add capacity, it's recursive, right? It increases the capacity of the existing array and then recursively calls itself, right? On the recursive call, right, it'll end up in the base case, I guess, right? And it'll just go ahead and increment the top index and then assign the elements to the top index. Okay. Now, whenever you do something with an array in Java, right? Unless you make unless your collection or whatever it is you're implementing, unless you decide that it should have a fixed size, right? It's a common thing that you have to reallocate, so make a larger array when you run out of capacity in the existing array, right? So in other words, this is very common, right? It's so common that the designers of the language library decided that they should put in a method that does all this for you, right? So instead of allocating a new array, writing a loop to copy all the elements, right? All of this is packaged up into a method for you. So there's a method called arrays copy of. Copy of will actually do more than what this does, right? So copy of will actually let you create and copy an existing array into a new array, right? Copy of will actually let you copy elements into a smaller array, right? So if you have an array of size 10, you can make a copy of it that's only size 5, right? The copy will have only the first 5 elements of the new array, right? If you try to copy an array of size 10 into an array of size 20, then the first elements in the array of size 20 will be the first element, will be the 10 elements from the first array, right? And the rest of the elements will be whatever their default value is, right? So copy of, if you have to do something like this, just use copy of, right? So instead of writing this, right, you can replace all of that code up there with one line, right? Simply write new array equals arrays copy of, right? So copy that array into a new array of that length, right? And that will take care of all of that. That will save you from having to write your own loop there. Not only will it save you from having to write the loop, this is probably faster. Because the way that copy of works, right? It doesn't actually use a loop. It uses a special method that can copy the contents of an array very quickly. Right? Okay, and then the rest of it just stays the same, right? All right. Now this array length times 2 business, right? So when you increase the capacity of the array, one of the things you have to decide is how much bigger should the new array be, right? You could just make it 1 bigger every time, right? And that would let you push another element onto the stack, right? Now what's the problem with doing that, right? So I make the array 1 bigger, I push the element onto the stack, right? The problem with doing that is if you then push another element onto the stack, you're out of capacity again, right? So now you're going to make the array 1 bigger, push the element onto the stack, right? And now the array is full again, right? If you call push again, well, now you have to make the array 1 bigger, right? And then push the element onto the stack, and again, it's full, right? So what you need to recognize here is that if you go back to the actual loop, right? If you have to increase the size of an array, so every time you increase the capacity of an array of size n, you end up doing n copies, right? You have to do n copies every time. So that's big O of n, right? The complexity of that's big O of n, right? So if you have to do this every time you run out of capacity, so if you increase the size of the array by 1 every time, right, then every time you push an element onto the stack, right, your push operation now becomes big O n, right, which is not good, right? So because you can do much better. Right? So you know that in an array list, adding to the end of the list is usually big O1. Right? And big O1 is a lot better than big ON. Right? So I can't emphasize how much better it is. Right? It's a lot better than big O of n. Right? So the question is how does array list do this? Because an array list is just a list that uses an array. Right? This is just a stack that uses an array. Right? It turns out if you increase the size, the capacity of the array, right, by not a constant, but instead by multiplying the current capacity by some factor that's bigger than 1, right, then on average, every time you push, or every time you add something to the end of the, well, every time you push something onto the stack, or every time you add something to an array-based list, right, then on average, the cost of doing that becomes O1, right? Every once in a while, it becomes ON, right? Because every once in a while, you have to increase the capacity of the array, right? So when you do that, that becomes ON, right? But if you multiply the capacity by some constant that's bigger than 1, right, you can actually prove that the complexity on average becomes O1, right? And that's actually how array list works. Right? So every time you add or insert into an array list, and the list is out of space, right? Internally, it resizes its array, right? And it resizes its array. I think the default implementation of array list increases the capacity by 1.5. It's either 1.5 or 1.25, right? It's usually not 2. The problem with 2 is you end up eating up a lot of memory that you might not need. Right? So if you have a stack of size 128 and then you increase its capacity, it becomes 256. Right? And you may not actually need all of that excess capacity. Right? So the standard library is a little bit more conservative than I am here. Right? So they use a factor that's smaller than 2. All right. Right? So again, remember, if you ever need to copy an array, you should use arrays copy of. Right? Because it will actually do the reallocation for you. All right, so that's, what time do we have here? Is it just 9? Yeah, it's just 9. So that's the end of that lecture there. And I think I'm going to stop there because the next thing I want to do is I want to make a linked list-based array. And I don't want to start that now and not be able to finish that because this is probably something many students haven't seen before. So I think I will end the class there, which is a little early, but that's fine. And we'll pick this up on Monday. There is an assignment coming out. It should come out in a few hours. The assignment due date on Q currently says it's Monday. It's not going to be Monday. It's going to be Friday or next Monday, the Monday after. All right. It's not long, so it's going to be of similar length to the current assignment. All right, but it will come out hopefully before noon. Right? I just have to finish up writing up the instructions for it. All right, thanks for coming. See you next week.